red giant star, if it's above a certain mass, around 5 times the mass of our sun, what happens is it can become unstable to a core explosion, which is a supernova explosion, and that can leave a remnant, which is a neutron star. But it can also, if the star is massive enough, leave a remnant that's actually not a neutron star, it's actually a black hole dimension. Okay, so the Cosmic Gamma Ray Observatory is designed to observe gamma rays. Now, when we talk about gamma rays, we're talking about photons that have an awful lot of energy, but photons also have something else we haven't even talked about before, which is momentum. Just like a speeding bullet, of course, has kinetic energy, it also has momentum. And when things have momentum, they're hard to direct or deflect in any way. They tend to just barrel through, right? So if you think about X-rays, X-rays have a lot of momentum, which is actually the reason they go through your body the way they do. X-rays penetrate normal flesh because each photon not only has a lot of energy, but it has a lot of momentum. This affects our ability to focus high energy radiation and form images. So here's an image made with the gamma rays of a galaxy that's kind of producing a tremendous amount of energy in the gamma ray range. This is a galaxy living out. Nothing like our galaxy. We probably couldn't live in a galaxy like this because the radiation tends to sterilize things. But you notice it's not really a super detailed image. And that's because there's a problem with actually focusing this kind of radiation that we're talking about now. We actually can't focus it directly using normal parabolic mirrors, glass mirrors. Because if you try to focus these gamma rays with a normal parabolic mirror, they will simply go right through the mirror. They'll just go right through the mirror because they have so much momentum. So what you have to do is you have to gradually coax them to focus by using what we call grazing incidence mirrors. And so what you actually have is a bunch of these sort of nested cone shapes. They're not cylinders, they're cones, but they're nested. And the incoming X-rays and gamma rays are just grazing against the mirror. So we're not presenting it perpendicular to the mirror, in which case it would go right through. We're just presenting it at a grazing incidence, and we gradually cause the rays to focus that way. We really couldn't do it any other way. So this is
the X-rays that Astro E2 will observe get absorbed in many materials, including glass and ordinary mirrors. So Astro E2 and other X-ray telescopes require a unique strategy to focus X-rays onto a detector.
We use an X-ray telescope, which depends on a grazing incidence reflection, in which the reflectors are nearly edge-on to the X-ray source. The X-ray beam hits the primary reflector, then hits the secondary reflector, and then moves on to the detector about 4.5 meters away. We add a pre-collimator before the primary reflection to block off-axis X-rays.
So you see the point there.
Pre-collimator before
the light again is coaxed to bend slightly by the sequence of nested cylindrical shaped mirrors. Okay, let's go on from there. Now, if we're looking at visual, we can look at the same object in space using different wavelengths to see what it looks like. If we just use visible light and we look at Orion, we see exactly this. Although with the unaided eye, we won't see all these stars. But we will see the belt stars and the main stars and the corners. And you can even see a little bit of this haziness with the unaided eye. This constellation is getting higher as we get closer to winter. And this little hazy patch that you can actually see without a telescope is the region where new stars are forming and glowing and actually causing that little cloud to glow there. Now, if we look at the same object, same part of the sky with X-rays, what we find is that we do see X-rays coming from stars. This already was a tremendous surprise, because remember that when you look at the sun, you're seeing a yellowish glow which corresponds to a temperature of about 6,000 Kelvin per second. Well, if you're going to get X-rays, you need temperatures on the order of at least 10 million Kelvin. So you're going from 6,000 to 10 million. So the thinking at the time that the first X-ray detector was flown in space was that this was just a complete folly. This isn't going to be anything out. There's no way that you could ever have anything that hot. And yet it turned out that just looking at ordinary stars actually emit X-rays. And this is actually something we still don't really understand very well, because they're not coming from the same part of the sun where the visible radiation is coming from. And we even see some X-rays coming from the Orion Nebula due to young stars. Okay, infrared astronomy using the space actually represents a dust cloud. It's a huge dust cloud from which all these stars probably form. And some of the star formation is actually still occurring now. And the reason I was seeing infrared, we understand now, is because these are these tiny little dust grains, which are just like the size of ordinary dust grains on Earth. They're all actually getting heated by the light from the stars. And they're getting heated to a certain temperature, and then they radiate based on the black body spectrum associated with their temperature. So it's kind of like a hot sidewalk on Earth in the summer. It's heated by solar radiation, but the sidewalk doesn't emit anything like the solar radiation, because the sidewalk doesn't reach a temperature of 6,000 Kelvin. It just reaches a temperature of about 300 Kelvin, and emits infrared radiation, so you can feel the hot sidewalk or the hot asphalt parking lot, because it's emitting infrared radiation as a black body spectrum. Well, these little dust grains are doing virtually exactly the same thing, although it's a little bit colder. But they're getting heated by the visible light of those stars, and they're reaching a certain temperature, and then they re-radiate infrared because that goes with the temperature that they've reached. And so what we're seeing is that infrared is this way to map out these huge dust clouds, and you see all kinds of structure. There's this, tremendous structure in this cloud that basically represents the history of it, the way that it evolved. This is only a tiny speck of our galaxy. Okay, so moving into longer wavelengths from infrared, we were just looking at, we get into radio. Well, radio telescopes are pretty much immune to the atmospheric blurring effect, essentially because they really don't interact with atmospheric gases much at all. Because the long wavelengths we're talking about really don't get refracted by the air because of the long wavelengths. Weather doesn't even really interfere with observations, and you can even do observations from the brain with radio telescope. I mean, overcast, you can do no problem. Because the radio waves pass through the clouds and they even pass through the water if it's raining. So because of this combination of factors, seeing for radio telescope is almost always at that theoretical limit. But the theoretical limit isn't really necessarily that good for radio telescope. We have to look at the formula to see what's going on with that. We can even make observations in daylight. So this is the single largest radio telescope in the world. It's in Arecibo, Puerto Rico, and it actually is built in a natural valley there. Now, normally with a telescope, you want to be able to point it, right? You want to be able to point it at some source that you want to look at. Well, they tried getting permission from Castro's government to actually point the whole valley, but he didn't really want to do that. So the valley kind of is stuck there that way. So the telescope basically just looks up from where it is. Natural pole-shaped telescope really can't be pointed. It does have a certain field of view, but as the Earth rotates, it just looks over the same swath of the sky over and over again as the Earth spins. But nonetheless, that's still interesting and worth having this telescope because it's so huge. It's very sensitive to faint sources. Now, you probably don't know this, but there also was actually a James Bond movie filmed partly in Arecibo, and in that movie, I think they have some part of the film where Arecibo gets flooded, the telescope gets flooded somehow, and the bad guys land there in a helicopter and do all kinds of strange things. But anyway, there's this one section which actually does kind of give you a flavor for the typical life of an astronomer. Let me just, if I can get this out there. Just a short, not this short.
Introduce.
Can't do anything about this one. Driven by a car. Wow, that's cool. So as I said, this part is kind of realistic than the life of an actual astronomer. There's the Arecibo telescope. Very competitive to get funding.
Ready to signal the satellite.
A lot of cutthroat competition. You get to get
Transmit about the entire.
Bad astronomers are the ones shooting. These are the good ones here. auditized version of the radio emissions coming from this object. So it's not really the sound. You take the radio waves and convert them to audio frequencies instead. So it's kind of cool because you can kind of hear some of the effects of the sound. This is our conception again. So that part at the end is the actual singularity at the dead center of the black hole. So if you tell it to the black hole, you finally know the answer to the mystery of black holes, which would be dead about a millionth of a second later. But really, that's the problem. You can't get into a block. You know what I mean? And even if you could, you wouldn't be able to get the block out because of the fact that you just passed through what we know as the event horizon. And once you pass through that event horizon, it's basically goodbye to the rest of the universe. Hello to the future of your life, which is only going to be a millionth of a second, which is why it's not really advisable, right? And you can't get the